Welcome to part 2 of our lecture series on facial recognition. Reminder that this lecture series requires OpenCV version 3.3 or greater. For instructions on upgrading your OpenCV version, refer back to lecture 1. In the first part of this lecture series, we explored this concept of the face as a mathematical representation, and we looked at the history of facial recognition in the context of developing our own facial recognition algorithms. We then utilized deep neural networks to create our own facial recognition algorithm that could detect faces in images. Here we'll take a look at applications that utilize this technology. For example, camera software on our smartphones will automatically identify faces in the image frame such that it can adjust the focus of the image and ensure that all faces are in focus in the recorded image. The ability to detect faces in an image is key to applications such as Snapchat. These applications identify the facial structure in an image and use those locations to overlay various filters. Security systems in our homes, such as the smart doorbell shown here, utilize facial recognition algorithms to detect the presence of faces and to predict the identity of the person outside of the house. With these applications in mind, let's now update our facial detection algorithm to detect the presence of a face or faces in a video feed. Let's begin by opening up our facial detection.py script, and we'll now update our argument parser to remove the image input argument and add an input argument for a video. So here we'll type ap.add_argument. Let's attach a -v or a --video as the input argument. We'll make this required for our detection algorithm. And let's tell the user path to video file. Let's now create a chunk of code that will automatically determine the dimensions of our video file. This will be advantageous down the road such that we can feed in any video of any dimensions into our facial detection algorithm. We'll begin by defining cap equal to our video capture, so that'll be cv2.videoCapture, and we'll feed the video location, the input argument, into cv2.videoCapture. We'll go ahead and read in a frame here. So we have check, comma, frame equals cap.read. Check will confirm there is a frame present, and if there is a frame present, frame will be populated with that matrix. Let's also define here a counter. This will keep track of how many frames are in the video file. So I'll initialize counter equals 0, and we'll also initialize a value of check. So we'll say check equals true with a capital T. Let's create a while loop that will continuously verify if frames are present. So we'll say while check double equals true. We'll read in a frame from the video file. That'll be check, comma, frame equals cap.read, left, right parenthesis. Let's grab the video dimensions from one of the first frames. So if counter equals 1, the height of the video file will be equal to frame.shape of 0, and the width of the video file will be equal to frame.shape of 1. We'll print those dimensions to the screen for the user, and then we'll increment counter. So we'll say counter plus equals 1. Finally here, let's determine the total number of frames in the video file. To do this, we'll need to subtract 1 from counter because the last time we attempted to read a frame from the video file, check would be equal to false. So we'll come down and say total frames equals counter minus 1, and we'll print this number to the screen. So we'll say print there are, comma, total frames, comma, frames in video file. This will tell the user how many frames to expect in the output video file. Here we define the output parameters. First, let's define our 4-character code. We'll say 4cc equals cv2.videowriter, capital V, capital W, underscore 4cc. We'll feed to this an asterisk, single quote, MP4, capital V, single quote. That'll output a .mp4 file. And then we'll define the output as well. So out equals cv2.videowriter. We'll pass a name for the video file. Here I call it facial detection underscore video.mp4. We'll pass the output code. That'll be 0x7634706D. And finally, we'll pass the frames per second as 30, and the dimensions of the video are width, comma, height. As you can see here then, we can now pass any video file into the script of any dimensions, and we can run this video through our facial detection algorithm. Let's now create a means to apply this detection algorithm to each frame of the video file, and then write that frame to the output MP4 file. So once again, we'll define cap equals cv2.videoCapture, and we'll pass the video argument to the video capture call. We'll type check comma frame equals cap.read. Check will again verify a frame is present, and if a frame is present, that frame will be populated in the variable frame as a matrix. We'll once again initialize the value of check equal to true. And we'll now define a frame counter that I'll call video underscore frame equals 0. Let's use another while loop here to loop through the entire video feeds. We'll say while video underscore frame less than total frames, read in a frame from the video file. So that'll be check comma image equals cap.read. Let's increment this video frame counter and print that to the console to give the user some sort of feedback about the progress of this algorithm. Since we won't be reading in images anymore, we can go ahead and remove this section of text. And now we want to construct the blob on each frame of the video file. So I'll type construct blob, and I'll now need to indent most of the following lines such that they are occurring each time through the while loop. Let's indent our for loop here. Again, we want to loop over the detections of each frame within the video file. For each detection, if it meets that threshold criteria for a minimum confidence level, we'll then continue with the bounding box. I'm going to go ahead and comment out the cv2.putText as well as the definition of the confidence level in text here, just to clean up the video file a bit. That all looks good. And then finally, we want to write this frame to file. So we'll write each frame of the video file, now pass through the detection algorithm out to an MP4. That'll be out.write of image. Since we're not showing an image anymore, let's go ahead and remove the cv2.imshow and the wait key. And then once we're finished, let's release cap, and we'll run a cv2.destroy all windows. That looks good. Let's go ahead and test out this script. In the Anaconda prompt now, let's replace the input argument from an image and now add the input argument as a video. So we'll add a -v and then feed the file name that you want to pass through the facial recognition algorithm and hit enter. Looks like there's 388 frames in this particular video file. We can see the algorithm being applied to each frame as the counter within the while loop is incremented. And there we go. Our video has finished processing. So let's head over to our folder that contains the video file and run this file. And it looks like we are able to successfully recognize a face in each frame of this video file. And based on that detection, we've added a bounding box to each frame of the video file. We now have the capability to recognize a face in a single image, as well as to pass a video file of any dimension and any length through our script to recognize faces in each frame of the video file. This capability opens up a wide variety of applications for facial recognition. Here we have an example of a video file recorded from a smart doorbell system. Notice that when the algorithm is able to detect a face in the video feed, it will draw a bounding box around that face. However, also take note of the limitations of this technology. Notice how many frames in the video feed do not result in a detection, therefore do not have a bounding box around the face. So you have to take this into account when designing your facial recognition algorithms and subsequent applications. Let's explore a particular application of facial detection in a video feed. Here the application will be implementing anonymity into a video feed such that when faces are detected, they are either covered or blurred. There's a whole host of reasons you may want to perform this type of anonymity in a video feed, particularly when trying to protect the privacy or identity of particular subjects in the video feed, such as minors or journalists or those being covered by journalists who may not have signed waivers permitting the recording of their faces or their identities in the video feed. And a particular application of anonymity of a video feed would be when evaluating various data sets, right? You may want to prevent the identity of certain individuals in the data set from being obtained. So a first step in providing anonymity in a video feed of this sort would be to implement the algorithm we've developed to detect faces in each frame of the video feed. We would then want to extract the region of interest. So essentially that bounding box and all the pixels contained inside that bounding box that identify a face. We can then color the box or blur the box using something like a Gaussian blur, and then take those blurred or colored pixels and effectively replace the region of interest with our colored or blurred pixels. So with that in mind, let's jump back into our algorithm and take a look at this type of application. Recall in our script that when we detect a face in an image or a frame of a video, we went through and drew a bounding box around each face. The coordinates contained within that bounding box, so from our starting x, starting y point down to our ending x, ending y point, that defines the ROI, the region of interest. So if we were to evaluate only those points in the image or the video frame, we could effectively color or cover the face, or we could apply a blurring algorithm to blur the face. So let's go ahead and start by coloring the region of interest with, in this case, a black box. So I'm going to come over here, I'm going to say, let's say, color the face area with a box. And what I'll do is I will define then those pixels in the region of interest as a particular color. In this case, we'll just go ahead and black out the pixels corresponding to that region of interest. So I'll come in here and I'll say image from starting y to ending y, comma, starting x to ending x. brackets. And we'll set those equal to 0, 0, 0. Of course, you could set those to any RGB value that you desire. Let's go ahead and save and run that script and take a look at the output. And here it is. So for each frame of the video in which we've made a detection of a face, we've gone ahead, you'll notice I've left the red bounding box simply for illustrative purposes. So our cv2.rectangle call is in red. And then inside we're covering the face, in this case, with a black box. Of course, you can set that to any color that you would desire. So of course, if I wanted just the black box covering the face in this case, I could simply comment out the cv2.rectangle call, and that would leave only the black box covering each frame of the video in which a face was detected. So this would be a great way to add anonymity to a video feed in the case where a face was detected in each frame. Now let's say instead of covering or coloring a face, or the region of interest for a face in a particular video frame, let's say you wanted to blur the face, right? So you wanted to take that region of interest and blur that detection. How would we do that? Well, let's implement that here. So here I'm going to say blur the ROI, region of interest. So let's define face area. That'll be equal to image of start Y to end Y, comma, start end to end X, start X to end X. I'll also come in here and blur that region of interest, right? I'm defining now effectively a new array that is the region of interest, that are those pixels effectively inside of that red rectangle, right? The pixels corresponding to our facial detection. So I'll go ahead and define that region of interest, and then let's apply a blur to that region of interest. Here I'll just run a simple cv2.blur. We'll call this face underscore area. Remember, we need to give it a kernel size. So let's start with something small. It has to be odd. Let's go 5 by 5, and I'll throw a 0 in there at the end. And then to replace the region of interest with the blurred face, I'm going to go through and do this pixel by pixel. Okay, so I'm going to replace the blurred region of interest into the original frame, pixel by pixel. So I'll say for I in range, this will be from 0 to face area dot shape of 1. And for j in range, from 0, comma, to face area dot shape of 0. What are we going to do? Well, we're simply going to replace the corresponding pixel in our original image, so the frame of the video, with the pixel from our blurred region of interest. So I'll say image start y plus j, comma, start x plus I. It's going to be equal to face area of j, comma, I. Now, of course, I've commented out the capability to color the region of interest. And so we'll start with simply the region of interest. I'm going to go ahead and leave the rectangle commented out as well so you can see the effect here. Now let's go ahead and save that and run it. And here we have it. We've now applied a blurring algorithm to the region of interest for each frame of the video in which we've detected a face. Now, because our kernel size is rather small, 5 by 5, the blurring, I would say, is insufficient, most likely, to properly mask the identity of the subject in the video here. So what we're going to do is come back to our code and increase the kernel size. So let's go from a 5 by 5 up to something like a 21 by 21. We'll save that and run it. Now we can really see the effect of increasing the kernel size on our blur algorithm. Again, for each frame of the video in which a face is detected, we've applied this blurring algorithm to the region of interest, then gone in and replaced the pixels corresponding to the region of interest in the original frame with the blurred output. And we see as we continue to increase the kernel size, we do a better and better job at blurring the region of interest and subsequently providing a better and better level of anonymity to each frame of the video.